In this lecture, we shall be talking about some of the unique, you can say, input output features that are available in the STM32 board, which you saw in our last lecture. The title of this lecture is PWM and the interrupts on the STM32F401 board. So, in this lecture we shall be first talking about pulse width modulation, which in short we call PWM, then how to use PWM on this specific particular board, and lastly how to use interrupts on this board. Okay. So, first let us talk about pulse width modulation, what it is exactly. Now, pulse width modulation is a technique where you can encode the value of a, you can say, some kind of digital value into an equivalent analog kind of a value, but not directly. There is an indirect way of encoding it. We shall be understanding it as this lecture proceeds. First, let us see exactly what is pulse width modulation. The first thing is that just using PWM we can generate some kind of rectangular digital waveform, which means something like this, a periodic waveform where a rectangular waveform will be going up and down, okay, and there will be a particular time period. This will be the time period, let us say t. So, this will continue. Now, the main variability here is that where PWM helps us in bringing some kind of, you can say, feature which is proportional to some parameter we are trying to encode, that comes from the on off behavior. Like when this waveform is high, we say it is on, and when it is low, we say it is off. So, the matter of interest is that for how long our waveform is on and for how long it is off, right. So, this output signal will alternate between on and off durations with a specific time period. Of course, this on time and off time will also be fixed for a particular case, all right. And this PWM, we shall see, it can be used in a variety of applications. Well, we can of course use for communication, data communication, and also for control applications, which we would be more interested in for embedded system design. Okay. And for communication applications, you can also use PWM to encode some information, but for our lecture, our scope of discussion here, we do not need to know that. Okay. Fine. Now, let us see how exactly PWM works. Well, in this waveform which is being generated by PWM, the time period is kept constant. So, we specify the time period. So, once we specify this time period, let us see, the time period is capital T, this will be kept constant, let us say. Now, depending on the parameter we want to encode, there is something we are trying to vary. So, what is that? It is the pulse width. Pulse width or the on time, let us call it T on. This T on is something which we are varying. This we are varying in proportion to some parameter that we want to encode, all right. And in this respect, we define something called the duty cycle of this rectangular waveform. The definition of duty cycle is, it is the proportion of the time the pulse is on expressed as a percentage. So, actually duty cycle is defined as the total time for which your pulse is on divided by the total time period or the pulse period multiplied by 100. Now, in this diagram, the pulse on time is T on divided by capital T is the time period, multiply by 100, that will give you the duty cycle. So, this duty cycle, because T is the maximum value of T on if you can have. So, the value of duty cycle, this will be a fraction, or if you multiply it by 100, it will be a some kind of a percentage varying from 1 to 100, right. Now, another thing to note with respect to PWM is that, well, whatever duty cycle you have some particular duty cycle. For any kind of waveform, you can define some average value. What is the average or DC value of the waveform? For those of you who know Fourier transform, if you take the Fourier transform of this waveform, you will get some amplitude at 0 level, that will be the DC component of this waveform. Now, let us assume this voltage is varying from 0 volts up to some maximum, let us say 5 volts, 0 volts to 5 volts. So, the average value shown by this dotted line in between, this will be some value between 0 and 5. Now, this average value will very much depend on how much time the pulse is on. So, more the on period, this dotted line will be moving up, but if the pulses are very narrow, very small value of T on, then this dotted line will move down. Okay. So, if the on time is small, the average value will go down, if it is large, average value will be high. So, essentially by controlling the duty cycle, by adjusting the duty cycle, we are essentially adjusting the average value of the waveform. Okay. Now, if you simply take an integral and take the average, you can compute the average value of the waveform over the time period t. So, integral over the time 0 to t, let us say one time period, f t let us say is this waveform dt. So, it is high for certain time t on and off for the remaining time. So, if you take the average and if you just calculate, you will get a value like this, where V h is the high level of voltage, V L is the low level of voltage. So, it is high for t on period of time, it will be low for t off, which is 1 minus t on period of time, because we are dividing by t. So, actually you can write t on t off here. And for most cases, the low level of voltage is taken to be the ground voltage 0 volt. So, if V L is 0, the second term will disappear, this will become 0. So, your average value will be only T on multiplied by V h. So, by adjusting T on, the average value will be becoming proportional to the on period or the duty cycle indirectly, right. If the time period is constant, duty cycle is proportional to T on, which in turn is proportional to the average value. Okay. Now, from this PWM waveform, how can we extract the average value? Well, the simplest way is you can use a low pass filter. The simplest kind of low pass filter is an RC circuit, a resistance in series and a capacitor in parallel. So, if you apply a pulse waveform, so you will be getting an output voltage which will be the DC value, provided the RC value, the RC time constant is chosen in a suitable way that only the lowest frequency components will be passed without any attenuation, the higher frequency will get attenuated. So, you will be getting approximately the DC value of the voltage in the output, right. Now, the interesting point to note is that this kind of a circuit with PWM you can use in place of a digital to analog converter. Now, a digital to analog converter, which we shall be discussing later, is a circuit which takes a digital input and produces a proportional analog voltage at the output. So, by controlling the digital input, we can adjust the output analog voltage. Now, PWM also provides you with a similar feature. like if you change the duty cycle of this waveform, that you can say is your some kind of digital input, you are adjusting T on and you are getting a voltage in the output which is proportional to that T on. So, this circuit also works something like a digital to analog converter. Just instead of applying a digital value in the input, I am applying a pulse width, I am adjusting the pulse width of the PWM waveform, right. Now, the point to note is that suppose I use this circuit to control some device, well it can be a heater, it can be a light where I am applying a pulse waveform to provide with the power supply. Most of the circuits have a built-in resistance and capacitance effect inside it. There will be some electronic circuit, there is an input impedance and there is often a built-in low pass filter in the input stage. So, this low pass filter often is not required for most cases. This PWM pulse waveform you can directly apply to the device you want to control and the low pass filter in the input stage will automatically extract the average value and based on the average value whatever you want will be done, right. Okay. So, some typical applications of PWM, well here I am listing only a few, you can think of other applications as well, there are many applications you can think of. Suppose you are trying to control a DC motor. So, for controlling a DC motor there is often a control signal. With the help of the control signal you can adjust the power supply you are applying to the motor. So, the power supply that is applied, if the PWM waveform you are applying directly, then the average value will be the equivalent power supply. So, by adjusting the duty cycle you are effectively adjusting the power supply, thereby you are adjusting the speed of the motor. Okay. This is one application you can think of. Suppose any light, well I am considering a LED light emitting diode, it can be any other lamp. So, if I apply a PWM waveform as the power supply of that lamp, so I can adjust the brightness level of the lamp, this is another application. Think of a gadget like heater or even you can think of microwave oven. So, when you adjust the power of the microwave oven, what actually happens? There is a PWM mechanism which will be switching the microwave mechanism on and off and the duty cycle is adjusted. Same is the case of an automatic heater control system. You turn on and off the heater, the time you are turning on the heater that will be proportional to the duty cycle of the PWM waveform. Okay? And there are many other similar applications you can think of. Now, if you revisit that board we saw in the last lecture, the STM32F401 board. Here if you look at, you note the Arduino connector because the same connections are available on the detail connectors also. But if you look at the Arduino connectors, you will see that there are several PWM pins which are mentioned. There are 6 such PWM pins which are mentioned. Okay. So, there is a standard PWM out interface that we shall be using some kind of software development platform called mbed, this we shall be seeing later. Under mbed, this PWM out is a standard library which is provided. It helps us in developing applications that uses PWM. Now, this interface has some functions which can be called to adjust the duty cycle of the PWM waveform that is being generated. Okay. Now, this Arduino interface, as I have just now shown, Arduino interface supports up to 6 PWM outputs, but if you have access to these detail pins, there are many more. So, you can have more than 6 PWM output pins also. Now, essentially this PWM signals on and off, these are generated using some timers. Well, you can put the output to 1, load the timer with a value, and with a clock the timer will be down counting, you wait till it goes 0. Like for example, this on period can represent a count value of 10 and this off period can represent a count value of 18, let us say. So, I will be loading the counter or the timer with that appropriate value and let it go on counting down till it reaches 0, and as soon as it reaches 0 I change the value of the signal, and this repeats 10, 18, 10, 18, 10, 18, and when I want to change the duty cycle, the total I will keep 28, but only I will be changing the first part. Suppose the first part I make 5, the second part will automatically get adjusted to 23. The sum will be 28 because period will remain same. Okay. So, these adjustments are done automatically internally as I adjust the duty cycle. Okay. So, let us look at the functions that are available as part of the PWM out library. So, I am just talking very briefly about it. This PWM out is the, you can say, the class. This is an object oriented concept. This is the class which will be creating a PWM out interface connected with a specified pin, because on the Arduino interface we will be seeing there are many pins which are called D1, D2, D3, D4, D5. So, whatever PWM pin you will see it is written PWM/D3. So, here you can specify that D3, that you are trying to use the D3 pin as your PWM out. Okay. I will take some example, and there are some functions called write and read. Using the write function, you can specify the duty cycle of the waveform. Duty cycle is specified as a fraction from 0 to 1. So, means it is not multiplied by 100, just on period divided by the total period. It is specified as a fraction. So, if you write it as 0.5, so it will be equal on period and equal off period. Okay. They will be symmetrical. Similarly, read, well, you can use read to read the current value of the duty cycle setting. Suppose in a program you do not remember what was the duty cycle you had set, you can call this function read and know that, well, my duty cycle was 0.5, let us say. Okay. And we can set the time period. There are 3 functions available: period, period underscore ms, period underscore us. The first one specifies the time period in seconds, second one specifies in milliseconds, third one in microseconds. The only point to notice that when you specify it in seconds, your parameter will be a floating point number. You can write 2.5. So, it will be 2.5 seconds, but when you specify in milliseconds and microseconds, the parameters will be integers. So, no fractional parts are allowed. You should remember this. Okay. So, you can set your period, you can set by write the duty cycle. So, your PWM will be generated. But instead of specifying the duty cycle, there is another way of having the control yourself with yourself. You can specify the pulse width, exactly what is the on time, T on. So, here also you can specify in seconds, milliseconds or microseconds. Again in seconds it will be floating point, milli and microseconds they will be integers. Now, write, there is a shortcut. If you straight away give the name of that object and equal to something, so that is equivalent to write. You can make a shortcut, and just name of the object if you use in an expression, that is equivalent to read. These are shortcuts. Okay. So, here we will take some examples how to use them. This is a simple example. Suppose we want to generate a 100 hertz pulse with 50% duty cycle. So, what is the meaning of 100 hertz? Suppose this is my pulse which is being generated, this is my time period. 100 hertz means 1 by 100 second will be the time period. 1 by 100 is how much? 0.01 second. So, you see the first alternative. So, I am showing here two alternate codes. The first alternate says I have to include this mbed.h header, because many of the functions I am using, they are all included in this embed header. This PWM out is the PWM object I told you. So, here you will have to create an instance of this class, you create an object, you call it PWM1, this is a name you are giving, and P21 is the name of the pin you are giving. P21 is the pin name. Okay. So, P21 is with respect to the original detailed connector, where you see there will be one connector on either sides. So, the convention is the pins are numbered like this 1, 2, 3, 4, 5, 6 like this, that pin number 21 is a PWM port, or if you use the Arduino connector, it is written PWM/D3. So, instead of P21 you can also write D3 straight away, or D9, sorry, P21 is D9, you can write D9 here, right, same thing. And in the main function, this is a C code I am writing. So, I am calling the two functions period and write. PWM.period is 0.01, which means 100 hertz, 1 by 100 seconds, and write I am specifying the duty cycle 0.5. The second code is the same one, where instead of calling write I am using the shortcut. If I write straight away PWM1 equal to 0.5, this means actually we are writing the duty cycle 0.5. This is just a shortcut. Okay. So, this is how you can generate a PWM waveform. Just another example, this is a 1 kilohertz pulse with 80% duty cycle. So, here the waveform will look something like this. First, it is 1 kilohertz. 1 kilohertz means the time period will be 1 by 1k, which is 1 milliseconds, and 80% will be the duty cycle. So, in the same way you specify a PWM pin, you specify the period in milliseconds, I am using here ms1. So, it is 1 milliseconds, and PWM equal to shortcut I am using duty cycle 0.8. So, it will be generating a waveform like this. Okay. So, this we shall be seeing in the demonstration, how we can use this PWM control to generate various kinds of waveforms. Okay. Now, let us see what are the kind of interrupt facilities that are available on the STM32 board, because you know that in many applications wherever you are interfacing some devices, there will be some devices which can be generating some interrupt signals from outside. So, I mentioned that in the ARM processors there are many interrupting source. In fact, any of the port lines you can use as an interrupt input, right. So, let us look into a little more detail. For the STM32F4 general family of boards, talking about external interrupts, there are 23 external interrupts that are supported, right. Now, among these 23 external interrupts, these are split into two sections. Now, in the first section we have the general purpose IO pins like the port A, port B, port C I talked about. I will show it in the next slide again. In the first part you have the general purpose IO pins which can be used as interrupt inputs. So, in the actual experiments we shall be using these pins only to connect interrupting sources. But there is another section, another part where some specific devices are generating interrupts, like your USB interface can generate an interrupt, your real time clock which is there, real time clock which maintains the time of day clock, that can generate an interrupt, some timer which you are using, that can generate an interrupt. If you are having a network interface like Ethernet, that interface can also generate an interrupt. So, these are device specific interrupts which fall in the second category, but first category is more general purpose. Okay. So, in our experiments we shall be using the first category. Now, in the first category, these are called general purpose IO or GPIO pin interrupt lines. Now, under this category, broadly speaking, we say that there are 16 interrupt lines. These interrupt lines are referred to as line 0 up to line 15. Now, you should remember that in this ARM board, this family of board that we are using, there are 3 general purpose IO ports, each of them are 16 bits. These are called port A, port B and port C. These are numbered from port A 0 to port A 15, port B 0 to 15, port C 0 to 15. Okay. Now, the point to note is that these 16 interrupt lines, they are not independently connected to all the port lines, rather line 0 is connected to PA0, PB0 and also PC0. So, when you are trying to use line 0, you can connect your interrupt input to either PA0 or PB0 or PC0. This also means you cannot use PA0 and PB0 as 2 separate interrupt inputs, because they actually mean the same line with respect to interrupt. Similarly, line 1 is connected to PA1, PB1, PC1, line 2 is connected to line 2, connected to PA2, PB2, PC2 and so on, right. Like this, the things are getting connected. So, as I said, you cannot use PAX, PBX, PCX for the same value of x as interrupt input, because PAX, PBX, PCX all refer to the same interrupt input line x. Okay. This is something you have to remember. There are 16 interrupting sources you can use, okay, at a time, but all the 48 port inputs you can use for the connection. Now, for the interrupt, the library functions that are available to us are as follows. Well, interrupt in is the class, you create an object of type interrupt in. So, here also you specify which pin you are trying to connect to, just like PWM, and these are the functions that are available. Read means you can read the status of the interrupt input, whether it is 0 or 1 currently. If you call read, you can read the input, it will come as either 0 or 1 of type integer. If you just use the name of the object you are creating, that is a shortcut for read, that way also you can use. And there is a function called rise, where as a parameter you give a pointer to a function. This means if there is a rising edge on the interrupt input, automatically that function will be called. So, essentially that function is like your interrupt service subroutine or the interrupt handler. So, when you are writing a C program, you can also specify for a particular interrupt input, this will be your interrupt handler. Okay. And you can enable and disable the interrupts by calling the functions enable IRQ, disable IRQ. Okay. This will enable and disable interrupts if you want. Okay. Let us show a simple example. So, on the left I am showing the code of a simple example using interrupts. Now, the instance that I am saying is that suppose this is your microcontroller board. So, on the line D3, let us say on line D3 I have connected a switch. So, how I have connected a switch? Typically we connect switches like this, we connect a resistance, then we connect a switch like this. On the other side we connect 5 volts and here we have resistance. So, if this switch is open, high voltage or logic 1 will come to D3, if it is pressed it will be shorted to ground, 0 will come. And on the other side in D2 we are connecting a light emitting diode. So, how we are connecting? Let us say we are connecting it like this. we are connecting a resistance, then we are connecting a light emitting diode, then we are connecting it to 5 volts. So, whenever D2 is 0, there will be a current flowing and the LED will glow. If D2 is 1, there will be no current flowing, because both sides will be a same voltage, LED will not glow. This is how I have made the connections, and what I want is that every time the switch is pressed, the glowing status of the LED should change. That means on, off, like that. With every press of the switch, the status of the LED should change. Let us see how we have written the program. First, as usual, we have included this mbed.h. Then we have created an object of type Interruptin. We have given the name switch. So, you can give any name, and we have connected it to D3. D3 is the pin number to which we have connected the interrupt input, and this LED is a digital output pin. There is another object that we use for that, it is called digital out. For all digital output port lines, we use this object of type digital out, and LED is the name of this connection, and here I have used D2, port number D2, and this is my main function. Let us see what we have done in the main function, this one. Here we have first made a call to this rise. Switch is the object we have created. Switch dot rise means I am calling this function in connection with the object switch, and I have given ampersand toggle, means address of toggle. Toggle is the name of a function, which means I told you whenever there is a rising edge on that interrupt input, automatically the function toggle will get called. And after that there is a dummy loop while 1, this is an infinite loop, your main program is waiting, and every time there is a switch press, means an interrupt is coming, what will happen? Toggle will just do LED equal to not LED. If LED was 0, it will become 1, if it is 1, it will become 0. So, for every switch press, toggle will be called and the status will change, okay? Just like this will go on. So, with this we come to the end of this lecture. Here we have tried to tell you about the PWM and the interrupt interfaces that are available on the STM32 board and how to use them. Thank you.